What else I'm going to see here? Okay, it's 1 o'clock. There we go. There's Derek. All right.
Howdy.
I'm going to get started if that's okay.
Please do.
Okay, great. Let's see if I can share the screen. Can you see this? Galaxy morphology, the low surface brightness universe. So I realized that I may have bitten off a little too much, more than I can chew with the title Low Surface Brightness Universe, because that implies that there's a lot to cover, and there is a lot to cover. But I'll just sort of constrain myself to just what happens around nearby galaxies, because that's an interest of mine, and that's so I know the most about it. And so we've talked about galaxies as if they're sort of this singular object, and they sort of look like that if you're on the sky or if you're looking at a small telescope and you're just using your eyes. It's a little fuzzy. There's no clear edge to them. And so it's a little unclear where galaxies stop, really. And we talked about that earlier. So where exactly does a profile stop? There is a natural edge to that, which is basically the surface brightness, the luminosity of the night sky. So the night sky isn't perfectly black. On a moon, even on a moonless night, it's not perfectly dark. And so there is a floor to however bright you can see. So again, if you have questions or comments, please send me an email. We should all be available on the CAS website soon. And so today is lecture 5. I'm really struggling with my, today's lecture 5, and we'll talk about the low surface brightness universe. So these are the galaxies that we think of, and we sort of think of those sort of as wheels most of the time, and like little footballs. And they're, even if there is no edge clearly for eye to see, we sort of impose an edge on these things anyway. And so as you look at them, even with Hubble Space Telescope pictures, it seems like, yeah, that's like it peters out, and that's sort of where it ends. So we have a tendency to just draw a line here and go, the galaxy stops here. And it doesn't matter what brightness you're talking about. At some point, you kind of can distinguish the last pieces, and it's like you draw an edge almost consciously, except that there is much more going on beyond this. So this is what we typically think of as the stellar disk. There is we sort of draw an edge to it, and then now I'm talking about what happens below it, right? What's on the shores of these, can't call these things island universes, and that's a very poetic term that has has been kept around. And so we talk about the shores of the island universes. The first thing to notice that there was something off, or like there was other things to see here, was if the people that studied edge-on galaxies, because we're looking edge-on, we're sort of integrating by the line of sight. So suddenly the whole disk is collapsed into a single small area, so you can start looking at the lower surface brightness features. And one of the things that Piet van der Kruijt noticed was that if you played with the contrast on this thing, that the disk would get thicker, but it wouldn't get any wider. And so there seemed to be like a clear edge to galaxy disks, and that was disk truncation. So anytime we worked on something like profiles, like we do here, you sort of assume that the profile would go on infinitely, but sort of with the understanding that you expect them to stop at some point, or it is physically unrealistic, right? So is that the scale that it go on, or it's simply at some point you hit one single star per kiloparsec, and it's like, are you really then still talking about a member of the galaxy or disk or not? And so that was part of the motivation to do this vertical profile, so that you can actually characterize what is part of the galaxy disks, and then also see what that fuzzy extra component was. Like, for example, the thick disk So it's a secondary exponential that you could see in the vertical perspective. So if you looked at these things edge on, it turns out that there's a thin disk and there's a second, fluffier, not as bright, thick disk. So thin and thick disks is a whole separate topic. So the question was like, does it simply go on? And even with digital cameras, like you can see, so you look at the surface brightness on the y-axis here, it goes down to 24th magnitude, and 24th magnitude per square arc second is sort of where the limit is if you look with typical digital cameras and a 2-meter class telescope. So it looks like, okay, that's our limit. And that's how well you can subtract the sky. And you can push it a little further down, but that's where it all ends. So disks, by definition, sort of end at 25 magnitudes per square arc seconds and not much further. So that would be a logical end to galaxies. So these really go to infinite radius, and so it's very difficult to tell because that's the night sky level. So essentially, you're subtracting one level from another, and it's very hard to say. Like if you over subtract the sky, the galaxy shrinks, and if you under subtract the sky, it's not really sure that the galaxy keeps growing. But with better and deeper images, something interesting starts to show up, and that is that disk truncation. So disks stop. They don't quite stop, but they basically switch to a different profile, to either shallower, that's type 3, or downbending typically, which is a type 2. So it's not so much that the disk ends, it's that the disk has, the exponential profile goes to a certain radius, and then there is scatter of stars out to further radii, which is, and so the stars all formed in a single disk, and then basically there's radial migration out, and that forms a second, much more lower surface brightness disk even further out. So that's one of the things that we think is happening. And so the low surface brightness universe, like the shores, these like shorelines of galaxies, that's interesting because there's clearly things happening. Okay, so they don't have the clear edges. So one of the problems we have, and if you there's actually much discussion about this in the book that I just finished, it is that galaxy disks, like how do you actually give a size to something that has a fuzzy edge, right? We can keep drawing this by eye, but then even no two people can agree on that. So we can say, well, this is where half the light is in. Well, then we are still stuck with where exactly is all the light then? Or do we have like a particular mass density that and so this is what these authors were doing. They tried to find something that would work on all kinds of galaxies, like big elliptical spiral galaxies, dwarf galaxies, so that we all get a good size measure for all galaxies, despite the fact that they're all fuzzy. So why do we go to the low surface brightness universe? The outer parts of galaxies have the longest timescales. So as soon as you see a statement like that, let's parse that. It means that because we're talking about really great distances, like if we're in the center of a galaxy, within the central kiloparsec, for example, everything happens pretty quickly because in a million years you can cross that, even with a reasonable amount of speed. If you do this with the kind of speeds that you have in the stellar halo, almost half a megaparsec across, say, for an object or something else to move from one side to the next, you need billions of years. So the timescales slow down. There's much longer timescales happening in the outskirts of these disks, which means that if you had to look at a tidal effect, the tidal effects take a while to take hold. If you're looking at something like a small galaxy being disrupted, that takes several billion years to do. And so in the outskirts of the galaxies is where the fossil records of their formation lie. And if you look at n-body simulations, that's what we're seeing. We see these streams of their original precursor galaxies, most of which have ended up in the galaxy itself, but there's little remnants of them orbiting at these really long timescale orbits. And so they're mostly like these streams are coherent still. And so we can look at them and see, oh, what kind of progenitor stars, what kind of progenitor galaxies fell into our galaxy or other galaxies in the way back when, like billions of years ago. So we can look at the ages of stars in these halos. We can look at how many stars are in the halo. They're all predictions from lambda CDM, so cold dark matter universe. So we have a cosmology, and then we put that in a computer, and that produces certain morphology of galaxies. And it produces a certain percentage of the stars in your model that ends up in like long-term orbits around your central galaxy. It predicts how long ago that was. It predicts how much metals there were in those early stars. So looking at the very outskirts of galaxies is galaxy archaeology. So this is one of two ways that you can actually identify how, or actually compare your observations to galaxy evolution models. So if you have a galaxy evolution model, you start at redshift infinity or like 20 or something, like your first bits of cloud of gas coalesce and become a galaxy, become a seed galaxy, and that acquires more stuff as more gas falls in, and maybe smaller galaxies fall in, and that goes on to the present day. And so you can look at all the intermediate stages with the Hubble Deep Field, like you can look back in time, just look as deep as you can and look at galaxies far away, and so those are from earlier epochs, so you can compare that. So that's one way to look at your galaxy evolution. But the other way is to look at the end product and see what's left in, say, the stellar halo. And so that's the galaxy archaeology. And those two things have to agree, because if they don't, then what's happening with our galaxy evolution models? So there are two techniques to do this. If you want to go down to really low surface brightnesses, so this is beneath the brightness of the night sky. It doesn't matter where you are on Earth. It doesn't even matter. You can still be in space, and the night sky will not be perfectly black. If you are looking in the optical and you're looking in near infrared, there's scatter of the dust clouds in our solar system. There is always another level of low surface brightness light that you have to go deal with that you weren't looking for. So you can either go deep, and so you take wide field optics, so fast optics. So these are wide field lenses, basically, and you integrate. You just expose and expose and expose until you go deeper and deeper and deeper into the night sky. This is something that you can do with a Schmidt telescope. So you need to have a camera that's optimized for wide field optics, and then integrate all the way down. So think hours or possibly nights on end. And then the other one is to look for, to resolve the stars in those faint structures around galaxies themselves. This is also hard because now you need a telescope that can do that. So you need, instead of having like wide field optics, very fast wide field telescope with fast optics, you now go to something with slow optics or and very long focal lengths, meant to resolve very, very faint small things. And so think the Hubble Space Telescope. So the Hubble Space Telescope can identify individual stars around nearby galaxies. And so you start counting those and convert that into a surface brightness. Both of these techniques are technically incredibly challenging, but they have different challenges. So you sort of go, well, let's try both and cancel them out. And that's basically been the approach. So this all got started, well, not so much started, but it really kicked off when there was a wide field multi-year project to image not just Andromeda itself, but the very wide area around Andromeda. Andromeda is almost a naked eye, or I think on a good dark side, it is a naked eye object, and it is it's the nearest spiral galaxy. And so with ground-based telescopes, so like the Isaac Newton telescope in La Palma, you can actually identify individual stars out to great distances away from Andromeda. And so that's what they started doing. And first you get with, at the top left, you get what they originally got, which was that you see all these structures at very low levels of light. So very hard to do with just a camera or anything. But you see these structures like these shelves, these streams, there's a plume coming out. So clearly there's something dynamic happening, dynamic on extremely long timescales again, but clearly Andromeda wasn't just this, meek, lovely disk, but actually lots of other interactions have happened, and we're basically looking at the remnants here. And so this is very annoying. So we're ending up with these lower surface brightnesses. So we kind of get these. They started off at the top level image. That's you can sort of see the little squares of the camera where they just tiled along very patiently to get star counts around Andromeda, because the prediction was from lambda CDM from cold dark matter models that galaxies like Andromeda and galaxies like our own Milky Way should have at least 100 satellite galaxies or so. So this was called the missing satellite problem, because we knew about 2 for our own Milky Way and 3 for Andromeda or something like that. And so 2 orders of magnitude, you can't even ignore that in astronomy. So let's go look for the low surface brightness satellites that models predict should be there. And what turned out is that those satellites, a lot of them basically got tidally disrupted and got smeared all over the sky. And so then you need to do star counts and look for those coherent structures. So after having done that first with a 2-meter class telescope, they moved to the Canadian French Hawaiian telescope, CFHT, on Hawaii, and Mauna Kea, and they did this much wider view on the right here and looked for further streams. And the thing is that the further out you look, you still see stars. There's still over densities. There's still coherent streams going along. So the actual extent of Andromeda is, you can see the little picture that you typically see, the background Mac icon, and then you see how big the actual stellar halo around it is and how many other structures there are in there. You see all these little loops and shells and streams and what have you. So this has been extensively studied, because now we can look at the stars and see what kind of metals they have, like look at these stars and estimate when they got acquired by Andromeda. So, but it's still one single galaxy. So we'd like to do this more often, and we'd like to do this with other nearby galaxies. So Martinez Delgado started a long-term project collaboration with amateur astronomers, and I think the term amateur really stopped applying here, because they have these wonderful setups in like pretty dark sky areas, and they have these 1-meter class telescope, maybe a little smaller, but they have wide field and they have good optics, they have good cameras, and they have time. And so they looked at individual galaxies for hours on end and just stacked all those images, carefully subtracting the sky every time, and then stacked them and stacked them and stacked them and stacked them. And this is what you then get. And so you realize that basically every nearby galaxy has had a smaller galaxy nearby be disrupted. You see these loops and you see these plumes and umbrellas, and there's these wonderful fanciful terms for these, but essentially all of them have eaten a Magellanic Cloud-sized galaxy and smeared it all over the sky. And so we're finding that this is very, very common. So much more violent history for all of these galaxies, but we're also looking at like how often this happen, how big are those plumes, how much do they hit bullseye, or is it like, is it typically like just a tidal event where they become these big loops? And so this has kind of been this long-term project, right? So it takes a while to do one of these, and then, just keep processing them. And as you can see, so top left is kind of the poster child for this. This is NGC 5907, the Needle Galaxy, and it has this wonderful double loop, right? So there's an astronomy picture of the day of that as well. It's just a little bit outside HST range for this, so I still want to do this so badly. But anyway, you can see that there's a double loop. So basically a little satellite came and got smeared all over the sky by tidal effects, by something called phase wrapping. Basically, the first stars that fell in accelerated the first, so their speeds, they sped up the first. So as it falls in, it elongates. And so you kind of get this trail of stars around a galaxy. The current estimate is that it took about 2 billion years for that interaction to do this. And so, yeah, that's a fossil record of something that happened or started happening 2 billion years ago. And you see all these other different plumes and structures and shells. Shells is another example where you actually hit straight through the center of a galaxy. And so you end up with all the stars sort of running out of speed. They've converted all their kinematic energy into potential energy again, and then going back. And so like oscillating back and forth through as they speed through the galaxy, through the center of the galaxy. The neat thing is that they encounter a little bit of friction every time they pass. So shells sort of interleave. And so you see these wonderful shell systems. Elliptical galaxies are well known for as well. This is a very recent result by the Martinez Delgado group, and I think this is wonderful. On the left is a picture done by a 40-centimeter telescope. That is not what you think of professional telescopes, but oh my gosh, they are great paired with a CCD. So the total integration of time here was, I think, 16 hours. So this is not for the faint-hearted. But as you can see, there's pretty clearly a loop around this. And that central galaxy, we know pretty well. That's the Sombrero Galaxy. So there is a satellite that was disrupted by the central potential of the Sombrero Galaxy. And you can model that. So they actually modeled the whole thing. And now we can go look, say, with an 8-meter class telescope at that faint fuzzy loop and see if the speeds are in fact as our model predicts. But this seems to dovetail very nicely with what models have been predicting. So at the bottom, you see the kind of loops that models, libraries of models have predicted for what happens when small satellites fall into bigger potentials. How often does that happen? And so the prediction was, you should be seeing that around every nearby galaxy. And the answer is, we are seeing that around every nearby galaxy. Some sort of some combination of the various morphologies you typically see. So that's good. But now we really want to have statistics on that to see how often do we see like a certain size satellite fall in, how long, how often does it happen, how many times, is it always one satellite or are there multiple satellites? Can we explain everything that we're seeing with just the one Magellanic Cloud getting disrupted, or do you need 5? So that's where we're getting now. The trouble is that this is very hard to do because our own Milky Way kind of throws our game. So what you see here looks like interesting events, but all that, that fuzzy stuff that you see around these galaxies. I love how they do this, by the way. There's basically a black and white image, and then they sort of superimpose the color image from the Sloan Digital Sky Survey. So because that's what we think of as galaxies. So you go like, oh, there's the galaxy, and then you realize and here's everything around that galaxy. In this case, that is dust. This is small fuzzy dust clouds, cirrus clouds of our own Milky Way. And they occur at high galactic latitudes. So it's not like you can look out of outside our galactic plane and then go, well, then dust is no longer a problem. These cirrus clouds are definitely there, and they're hard to account for, especially if you're looking for loops and interesting things. Like what exactly on the left here is a loop and what part of that is cirrus. So you have to go look at other wavelengths again. Galactic cirrus is pretty much everywhere, so the problem doesn't go away. This is a picture from the Dragonfly website. You can see that there are some dark windows here and there, and so that's what we typically use for extragalactic work. We go for a place where there's as little dust by our own Milky Way as possible, but if you want to do low surface brightness, you don't really have that luxury. You have to go and account for this dust glow. So sky subtraction sort of encompasses both the glow from cirrus as well as the dust in our own solar system, stuff that's being left over by comets and what have you, as well as whatever the night sky, which is the actual sky, throws at you. So there's typically just a gradient, there's like a lower level where you get light or a light gradient across your image. And so you have to keep tabs on that, right? So you have to remove all the individual sources and then model what you see on the top right here, the sky gradient. So there's not just a a single level, there's typically a gradient, possibly even like not just a slope, but actually multiple gradients. And then you have to model that very carefully and then subtract it, because otherwise, yeah, you've just sort of added a whole loop on one side. It doesn't mimic, except for the galactic series, it doesn't mimic sky subtraction, does not mimic the structure that much, but it definitely mimics, extended profiles, or like an upbending. If you did your sky subtraction wrong, you can end up with like an upbending profile, or you did it wrong the other way, and then suddenly you go like, oh, it's truncated. No, you were too enthusiastic with the sky subtraction. And there is also something called a PSF. And so the PSF is the point spread function of your optics. Whatever you're using, it is not perfect optics. We try to approximate perfect optics, but shall never have them. And also, because we have things like struts holding up secondary mirrors, and because we have blemishes in the mirrors themselves, and because of quantum effects, basically, you always have a little bit of interferometry. So what you end up is that a thing that's actually a mathematical point gets spread out over the image. And so anything you can, so you see top right is the, top left is the original, and then you look at one galaxy, you're like, okay, that's where it is. And now for each of those stars, you can see that they have like this they look six-pointed, right? That is the effect of the struts and the asymmetries in the optics. So what you end up doing is modeling that two-dimensional distribution of light. Those are stars, they're effectively point sources in for our image. Like that's how it comes in, but our optics smear them out and turn them into that six-pointed thing. So you need to model that six-pointed thing in order to remove and look how far out the stars actually have effect. And especially the more interested you are in lower and lower surface brightness, which is basically what we're pushing, the further and further out these PSF effects are noticeable. So you have a bright source in your field, yep, then you have to remove all that stuff. You have the galaxies themselves are pretty bright sources. So the PSF moves some of that light to the outskirts. And you have to account for that. Because if you don't, you come back and say, oh, I have this wonderful stellar halo. It's very smooth. Well, it's a bit six-pointed, and that should already tell you something. It's a little pointy, but it's just around this galaxy with this really bright source in the center, and I found this halo around it. No. You just found the light that was missing from the center that got scattered by your telescope. So it's another thing to really take care of. So the idea, it started pretty much with the SESS. With SESS, it turns out you can already look at galaxies and start to push down the surface brightness, provided you're okay integrating. But the sky subtraction on the Sloan Digital Sky Survey is superb, simply because they use the drift scan method. So they actually, their sky variation is very minimal. So 26 magnitude per arc second is as far as you can push Sloan. Then you can go to almost 29 if you use Stripe 82, which is a special area that they actually push deeper and deeper on. And then you go to the CFHT, which is a 4-meter class telescope, so basically up the size of the telescope, bigger light bucket. You go to 29, and then GTC means Granticam, which is the 8-meter class telescope on the Palma. And so they can push that even further, 31.5. So beyond 30 magnitudes per arc second is where the magic starts to happen, because that's where we expect all those remnants to be. So basically beyond 30 to 35 is where, like, that's the surface brightness levels where we expect all those satellites to be, all those streams to be, the stellar halo to be. So instead of using existing telescopes, what would happen if we actually optimize our optics for just low surface brightness? So this is what the reasoning was behind the Dragonfly telephoto lens array. Now, this is one of those wonderful things where if astronomers have hobbies, they come up with really fun ideas. These are commercial lenses. These are essentially made for macro photography and sports photography, especially for sports photography. And so they needed good lenses. And so the latest Canon lenses and plus their coatings were let so much light through that they actually have astronomical use. So if you hear an astronomer say, oh, by the way, professional astronomers do not use refractors, telescopes with lenses in them, they don't use those anymore. Yes, we do. Yes, we do, for very specific things. So the good news about lenses is that there is not that much in the way of supporting structure. So there aren't that many diffraction spikes on your stars. So those go away and the optics are pretty fast. And then you just need to add a whole bunch of them together in order to make a telescope. So that's that weird insectoid looking telescope that you're seeing in the bottom left there. So this is taken off. There's a couple more telescopes that are built on the same principle. And so looking at nearby galaxies and then looking at the low surface brightness universe around them. And at the bottom right, you can see M31, Andromeda, from the star counts. And so you can see the shelf and the northern spur and all these other things sticking out. And you go like, oh, no, I can directly compare them to nearby galaxies. So I thought this was a very clever solution. So you can do things like you can now start pushing this to 30th magnitude per arc second or lower, and even get color information. So you can start learning about these. You can start learning about what the profile looks like, what's the color of the average color of the stars in the outskirts of galaxies. This has not been without controversies. Of course, there's multiple groups now working on this. So for one thing, the Dragonfly telescope reported that M101 had an anemic halo. That was their kind way of saying it was about 1% of all the stars. We expect about 10% of all the stars in a galaxy that size to be in the diffuse outer halos. And M101 wasn't having it, so that was the first thing to look at. Some of those loops around NGC 5907 that I showed that earlier from Martinez Delgado, from Martinez Delgado in 2008, you see that double loop. But if they looked at it with the Dragonfly, one of the loops disappeared. So what gives? So some of this stuff has not been independently confirmed yet, or it's simply a matter of maybe that was a bit of glare in one telescope, and since the other telescope was a completely different design, it didn't have glare at that point. And a third thing that happened was ultra diffuse galaxies. Now I can basically talk about ultra diffuse galaxies for the rest of the talk, so I'm mostly skipping over that. But ultra diffuse galaxies are effectively, I'll talk about that in a little bit, but they are a new class of very low surface brightness galaxies. So here we are. This is what they look like. Not terribly exciting as galaxies go. It sort of looks like a very distant elliptical. And so if you see these in nearby deep fields, for example, you sort of dismiss them as either an artifact, as either something, oh, that looks like not the entire inside of the tube. There's a bit of paint that flaked off and there's a little bit of light that's scattered off or something like that. They look like artifacts, or they look like so distant galaxies that, okay, fine. But what turns out is that these things are pretty close. They're really just failed galaxies. They're just really low surface brightness. Low surface brightness comes in and out of vogue, and this is basically, we're in vogue now. And if you ask some people that did this 15 years ago, they go like, yeah, we call these things LSB dwarfs. They're not that new, but this is the new term for them, ultra diffuse galaxies. So very fuzzy, faint. The whole thing is basically 28th magnitude per square arc second. So this is what happens. You look at a group of galaxies, you got a couple of your bright NGC numbers there, and then a couple of other ones that are basically found with Dragonfly as little diffuse smudges. And especially you see it in one, you see it with Dragonfly, then you go to another telescope to make sure that you see some light there as well, right? They have to be independently confirmed. And typically HST has looked at these. And so these are HST ACS fields. Exciting. It's a little faint fuzzy thing. And so we don't even resolve these things in individual stars yet. So spectroscopy has revealed that some of these things, DF2 is especially controversial because The initial claim was that it essentially had no dark matter. That was based on kinematics. That looked pretty solid, except it was based on 10 data points. But it's all, no, there's very little light to go off there. So it's very hard to confirm that in an individual galaxy. So far, so good, but I think we should study more of these ultra diffuse galaxies. Meanwhile, my focus kind of went on to that M101 claim where Dragonfly said, hey, by the way, there is no stellar halo here. And so this was an HST proposal to go look for star counts in the halo of M101. The prediction being you're not going to find much. And so the way this works is that you have these little fields. So you see F1 through F9. And so these are HST, these are Hubble camera positions. So the red ones is the advanced camera for surveys. The blue one is, the purple one is the wide field camera 3. Hubble can look on one position with both at the same time. So, you gain a little bit there, but you see how small they are with respect of the rest of this galaxy. So if you want to do the whole halo, we'd still be doing this. So you kind of sample as you go along. I think of this, the archaeology analogy is very good because preferably if you're an archaeologist, you see this interesting, burial mound, you go like, great, I'm starting at the top and I'm slicing this thing all the way down to the bedrock and I'm going to find everything that's in there. Unfortunately, I do not have infinite funding. So what do I do instead? And so you kind of do a couple of trenches or plumb lines so that you can actually do proper work and figure out what you see underneath here, but you don't get a complete picture. You only get sampling as you go. So that's exactly how this happens. So we look for, we make a color magnitude diagram. So we find the individual stars, we have a color for them. This, in this case, the F606 and F814W filters with V band and Johnson I band. And so we make a color magnitude diagram. And that color magnitude diagram has a couple of concentrations in there. So you've got the main sequence, which is all the way on the left, so around value color of 0. And then you have the RGB, which is the red giant branch, the AGB, the asymptotic giant branch, and you've got the helium burning branches as well. So what we're looking for is mostly the red giant branch. A, there's a lot of them, so they're easier to count. And B, they kind of cut off at a very particular luminosity, so you actually can find the distance as well, based on where the what the parent luminosity, the RGB branch cuts off. But we can go count them all and then turn the counts of RGB stars into a light profile. So this is what that looks like. This is what the actual data looks like. And so as soon as you start moving away from it, you are left with like dozens of stars. So it is quite tricky to make sure that you've got them all, that you have checked for completeness. And this is sort of at the limit of what Hubble Space Telescope can do. But we found the RGBs, the AGBs, and we found the main sequence. And so you can make a profile in all three kinds of stars. So where the main sequence stars, the sort of the younger stars, the asymptotic giant branches are the intermediate ages, and the RGB are the oldest, if I remember correctly. And so you can do all three kinds of stars and then look for the profile. So you basically plumb along the axis here. And so you plot this as a function of radius from the center of the galaxy and see what the profile looks like. Then you take the dragonfly and the dragonfly profile on either side, and then you look at where your RGB counts lie, and they line up very, very well. So the gray lines here are what we find from integrated light. So that was one technique. The black points are what we find from star counts. And so combining those two, you see that it turns up a little bit. And that's the blue line is the outer disk profile, and then the red line is what we expect for a stellar halo. And so, yes, there is a stellar halo, but we are agreeing with what the dragonfly people found, which was that the halo is anemic. It is very, very low fraction of stars is actually moving in that halo. that kind of puts M101 at the weird spot because we have these models and they predict that about 10% of the halo should be, sorry, 10% of all the stars should be in that halo. You don't see them because they're smeared out over a much greater area, but about 10% of the stellar mass should be in the halo. And here we are looking at something that has like much less, like a 0.3% or something. So you can see the fraction of the halo mass in the of total stellar galaxy mass, and then the total as a function, oh, sorry. On the left, in panel A, you see the halo over a galaxy stellar mass. And so that's the fraction that's in this of all the stars stellar mass that's in the halo. And M101 is all the way at the bottom. We found a couple of other measurements. So a lot of that is from the GHOST program that uses HST star counts and then converts those into halo estimates, halo mass estimates. And on the x-axis, you see mgal, which is basically the stellar mass for the whole galaxy. And M101 is, as you can see, it's all the way at the bottom. You've got the green boxes and the pink box and the yellow box, and those are three different models of what you expect. Oh, and the red big from Bullock and Johnson from 2005. So you've got these multiple models for different ranges, but you expect typical galaxies to sort of live in there. And most of the points seem to agree. M101 seems to be a little bit of the exception. So it'll be very interesting to see if we get some more statistics on this, because that's just a few points and a few models, and you can always have an outlier. You can also look at disk truncation. So actually at what happens at the edge of a galaxy there. And so this is from David Radburn-Smith's paper. We also do the same thing, young stars, intermediate stars, and old stars, the RGB stars and the old stars again. And so we look at how strongly the disk truncates. And the old stars is the weakest truncation, and the young stars is like the clearest break. And so that's really interesting because that means, yes, if over time you scatter stars out, and so that sort of smooths out your disk break. So all these things happen when you have access to the low surface brightness universe. You can also look at, say, a warp disk. So warps happen in gas mostly. You can also see them sometimes in stars or other interstellar matter tracers, but gas is the best tracer. And early on, Piet van der Kruijt already pointed out, like, hey, that point where the disk truncation happens, that always seems to be the point where the warp starts. Maybe those two things know about each other. And so you can look at like that little corner there with that was the advanced camera for survey pointing with Hubble and looking at the old stars. The old stars seem to just stop and then go to that the disk truncation happens there, but the young stars seem to follow the gas distribution. And the way David interpreted that was that the gas is currently, like the reason that you're getting this warp in this particular galaxy was that the gas is falling in, and as it's falling in, it's also helping to form stars. So that's where the young stars follow the gas. The trouble is that there's more than one way to warp a gas disk. And we repeat the experiment, and then suddenly, yeah, you don't see this. So that's often the problem with galaxy morphology. There's always 2 ways or 3 ways or 5 ways to make the same thing, the same result, the same looking result, or roughly looking result. But at any rate, you can see that you can start following really low surface brightness effects if you can count the stars. Another example is, for example, here is dwarf galaxies. So this is from Wimbledon 2012, and that's a single advanced camera for survey picture on the left here, and you can turn that into sort of a image to the bottom right there. You sort of, the intermediate stages are at the top, where you count the number of RGB stars that you see in like little squares, and you turn that into like densities, and suddenly you end up with something that you can barely make out in the HST image. Oh, there's the morphology of this little dwarf galaxy that's nearby. And so you can also do this from the ground. And so ground-based surveys have been looking for like these loose associations of stars. And the most recent dark energy survey results are all reporting multiple satellites for our Milky Way, and they're all sort of like this. They're all these little fuzzy things. They're loose associations of stars. It's very hard for your eye to go, yeah, that's a galaxy. But if you process it like this, we isolate the stars that are RGBs, for example, at this particular distance, and you can say, oh, this is an overdensity of these things. That's actually a dwarf galaxy. They just don't look it. And so I want to do one more thing, which is that another trick you can do, you can say, well, the night sky is pretty dark if I look at just H alpha. And so the H alpha line, I have a very narrow band filter and I stick it on a big telescope, and I can then look at a nearby galaxy and I can see where the star formation is happening. This is glowing gas. So H alpha filters are to isolate star formation in nearby galaxies. But what Annette Ferguson noticed was that there are these little blobs outside where you typically would draw the line. This is where the galaxy ends. She looked at them at greater depths and noticed that, yeah, the spiral pattern seems to keep going in little connected H alpha clouds. And so that was confirmed a little bit later by Galax, this is Gilda Pass and Filker, and they all went through the Galax deep imaging and noticed that, yes, these spiral arms kept going. And so we call these now extended ultraviolet disks. You see that both in basically in H alpha, but you also see it in the ultraviolet. So there is star formation even happening way out. Yeah, but again, because everything is smeared out over greater distances, you can only really pick that up either if you have a special wavelength like ultraviolet, or you integrate for very long times, or possibly both. So you need to, the low surface brightness universe has a lot of things happening in it. And the interest now is very much, what does it tell us? And it's sort of the end state, like we're looking at nearby galaxies, which means that that's the end state of evolution at this present time. So if we make galaxy evolution models, they should have that low surface brightness archaeological remnants around them. If not, then the model's off. And so you can also use H1 for that. This is something that I'm a big proponent of, which is that because the ultraviolet is loose individual points, it's very hard to say, oh, that's actually belongs to this galaxy, that one doesn't. Just drawing the outer contour in H1 means that you can then say, okay, that the red dot here is every time that's the outermost H2 region. That's the outermost star forming region in each of these galaxies. So to summarize, the low surface brightness universe is incredibly interesting. It has all these, has this big archaeological findings in, it has the fossil record for all of these nearby galaxies. And so if you want to know how often did it merge, you can look at it and count the number of streams, for example. How big were they, right? So you can look at how long each of those arcs are. Like typically, if it extends 2 pi across the sky, you can go and go like, well, this is about half an arc. That's about a gigayear. And so you can compare those directly against n-body simulations. The easiest thing to do is disrupt a small galaxy in an n-body simulation and see where it ends up. Like that part is, I say easiest, and now somebody's gonna email me about that, but it is a lot more straightforward to see what happens to a small galaxy in a big potential rather than trying to figure out what happens to all its gas. So the stars are a little easier to do than the gas. And so that's why we focus on the stellar remnants. It can be very observationally challenging. We are talking both sky subtraction and PSF effects. So those are things that are very hard to do. You need to be very careful on subtracting the sky correctly and accounting for the PSF correctly. But on the other hand, it is also something that you have to invest a lot of telescope time in, and that can be not so much technically challenging, but you just have to convince people to say, hey, I need this particular telescope for the next few days. Please let me have it. And so you can do that both with dedicated telescopes. So that seems to be a very good approach with the Dragonfly, but also our colleagues in Ohio have a Schmidt telescope with a good wide camera, so you can actually dedicate nights upon nights to look at a particular group of galaxies or one particular galaxy. But the other one is to do star counts, and star counts for very nearby galaxies you can do from the ground, but most of the time you need Hubble. And so that makes it very expensive because Hubble can only look at a very small chunk of it. And so if you want to, even if you want to do a couple of plumb points, you need to have more than one exposure. So this adds up very quickly. Now, speaking towards the future, the Vera Rubin Observatory, that is an 8-meter class, low surface brightness. Well, basically, it's a giant light bucket. And it's a wide field optics, fast, so it actually is optimized for survey, but that also means it's optimized for low surface brightness, which means that we're going to get a very good low surface brightness view of the nearby universe in the southern hemisphere after 5 years of operations. You just stack all the images. So that's exciting. It's to a point that the Rubin Observatory doesn't actually think of dark sky anymore because there's going to be something in the image. It's either going to be a low surface brightness effect, or there's going to be scatter, or it's going to be cirrus, or it's going to be an object. Nobody really thinks of like, oh, that's dark sky. That might be a pixel. The other thing is that Euclid and the Roman Space Telescope, so these are the new Hubble follow-up, basically, or Hubble successors. These are 2-meter class telescopes. Euclid's 60 centimeters, I think. But these are near-infrared telescopes that would be great for star counts. So Vera Rubin is the observatory will be the integrated light approach, and Euclid and Roman will basically be the star count approaches, and then we can actually look across and see what each of them see. So we're going to get a very we're going to see a very good look at the low surface brightness universe very, very soon. And I'm excited about this because that's what all the fossil records are. I like to do fossil records or archaeological records. I like archaeological records. So that's what we're going to see. That's going to be a very good way to do galaxy evolution and compare against galaxy evolution models. So thank you very much. Let's see if I do for time. Oh, perfect. So thank you so much. I will post this soon. Are there any questions?
Thank you, Ben. Hey, what about the ELTs? Would that help you, the ESO ELT? Or is that not, something appropriate for this because the field of view might be too small?
Yeah, so the ELT, perhaps aided by adaptive optics, might do star counts, but the field of view is so small. And we've really found this with HST that if you're looking for these like streams of galaxies, so let's, here we go. So if you look at this, those streams happen to be about the width of the HST camera. So you see an increase of star counts, but then you actually have to have a second pointing on either side, or second and a third pointing to say, hey, is that an actual elevation in the numbers, or is just this halo a little, crowded?
Yeah.
And so it's very tricky to find streams like that. The integrated light is good for finding streams, but if you then want to characterize them, you want to. I didn't even talk about this, but the red giant branch. The slope on the color magnitude diagram tells you the metallicity of the stream. So you can say, oh, hang on, this was a -1, so very subsolar metallicity stream. That means the progenitor galaxy was X in size. And so you have a mass for the progenitor, and then you have a and this is how big the stream is. Oh, this must have happened like 2 gigayears ago. And so you have a data point on how often do galaxies of this size merge with stuff? And one single one is okay, but as soon as you start getting statistics like this, you can go, how often does this happen? And you can compare that directly to galaxy evolution models. So if they merge stuff too often, then you're like, yeah, I'm sorry, your model is great and all, but it doesn't reproduce what we see. So that's really looking like a very good approach to galaxy evolution.
Okay.
So yeah, ELTs are great, but not for
this.
Probably follow-up. So it's, again, you find the stream, you put a spectrograph. Like if I want to get spectra of these things, I need a huge light bucket. So
Right.
that's where the ELTs will come in, but not for discovery.
Yeah, then the smaller ones are actually better than when you have a dedicated telescope like Dragonfly.
Yeah, I mean, Dragonfly is a 1 meter telescope.
Mm-hmm.
This was done with a 40 centimeter telescope.
Yeah, yeah.
It just takes time and processing. I've been looking at if you could do this with TESS. The answer is, in principle, yes, but you have to account for the TESS PSF, which was not made for this. So it is, but it is a lens optics in space. So that sounds great. The problem is it's a little towards the red, which means that you get lots of scattered light from the cirrus. And the pixels in the PSF are huge. So it's a little harder to do this. It'll take a lot of post-processing.
Okay.
So, any questions?
Well, thank you, Benna. See you next week, I guess.
See you next week. I'll post these soon. All right. Thanks for coming.
Okay, bye.